Okay, so what we want to do is look very quickly at upper atmospheric winds. Now, these are winds in the upper atmosphere, okay, that are usually above the 500 millibar isobaric surface. Because remember, as we go up, well, I'll explain that in a second. Okay, so where you have areas of high pressure, those are called ridges because they go up, and areas of low pressure, they are troughs. So you have to think of this in like three dimensions, like they do in weather. Even though it's a two-dimensional weather map, you have to think of it in three dimensions in the real world. So as you go up in altitude, in elevation, the air pressure decreases. So what this map shows you is it's the base map is 500 millibar height. So it just shows you where every line is, well, every line is 500 millibars. And then what it shows you is the elevation for an isoline showing the elevation for that 500 millibars. And you can see again that the closer the lines are, the wind speeds are going to be higher. Where they go down like this, it's a trough. Where they go up, it's a ridge. So the troughs are usually low pressures and the high pressures are the ridges. Okay, so here's what it looks like in a more of a 3D look. So you're showing it at 500 millibars, but notice how it's 500 millibars up here at almost 19,000 feet. Then it goes down to the trough to where it's 500 millibars at almost 18,000 feet. So that's like 1,000 feet in elevation difference. Okay, and trace the winds going around it with your high pressure and your low pressure. Okay, we call these Rossby waves that form along the polar front, and they basically are responsible for the polar vortex. There was one in 2014, and we're experiencing one, not we, but the people back east are experiencing one right now. Due to the fact that they travel further south than usual, carrying that heavy, dense cold air with them. And there's two animations in the course module you need to watch, one on the jet stream and one on the Rossby waves. So make sure you watch those. They'll show you how they work in an animated form so you can follow along and get an idea of the concept there. So here's the North Pole. Again, cold, dense air. It's the polar high. Presses down, carries that cold air with it. And the winds that travel along where the cold, dense air meets the warmer air down here, and that forms our pressure systems. These are the Rossby waves, and the winds themselves are called the jet stream. Because when you see the animation, you'll see that these move, constantly. They're not static. They look like waves the way they move around. So you can see your trough here, and then your ridge up here. Now, the jet stream are the winds that influence the surface weather. So that polar jet stream is between 30 degrees and 70 degrees north, and it steers the cold air south. And the subtropical jet stream between 20 and 50 north can happen at the same time as the polar jet stream. Whoops. Okay, and that's what that looks like. So here's the polar jet stream. Again, so the Rossby waves are this constantly fluctuating movement of the air, and the polar jet stream is the wind that forms along those pressure systems, the high up here where the ridge is, and the low down here where the trough is. And then you'll get a second jet stream, the subtropical one, a little further south. It's a little less powerful, but it still, helps move the air around. Okay, so again, watch those animations on course homepage there in the modules. They'll help you understand this in the animation. Now, the book also talks, and you're going to have exercises on this in mastering, about land and sea breezes. And they form from differences in land and water heating. That's a very important concept to understand. Land heats faster than water does because land, the sun goes down about maybe 15 inches, but in water it can go down, because water is transparent, can go down about 200 feet. So it takes much longer to warm up the water, but because it's a much larger volume, the water can hold much more heat. So what happens is the land warms up, then warm air rises, creating a low pressure. The air converges in and rises up. That's your low pressure, and it pulls in the breeze from offshore. And it's just this circular motion. The warm air cools, then descends, and just moves back and forth. This is what happens in the daytime, usually around 3 or 4 o'clock. And those of us that live by the coast, you can experience this on a daily basis. Then at night, when the air cools, it drops down as a high pressure. It's up in the upper atmosphere, pulls down and diverges outward and goes offshore. So that's your offshore breeze. So during the day, we get onshore. During the night, we get the offshore breezes. We have mountain valley breezes around here, again, because we're close to some mountains. The air cools very rapidly at night, and the valley air heats during the day. So during the day, the warm air rises upslope, and at night, the cold air moves downslope. So during the day, warms up, air rises up, and it takes the path of least resistance, which is generally the valleys. So it's going to move through these valleys. Then at night, same principle. The air cools down, it's heavier, denser, follows the path of least resistance, which are these valleys, and you get these valley breezes moving downward at night, downslope at night. Now the Santa Ana winds are what we have here in California, these very strong dry winds that flow across the desert towards the cooler Southern California areas. The high pressure, it builds over the Great Basin, which is on the other side of the Sierras. And it moves through, they're very powerful. They move down into the canyons, and as they do so, you get a lot of air going into a thin opening, and that speeds up the velocity and warms them up. So they get very warm and very high speed winds. And as we know, they can very much influence the spread of wildfires. There's nothing on the test about this, but it's very interesting because it's called the devil wind. It's just a little video that kind of shows you how these Santa Ana winds work. So here's the Great Basin over here, flows down over the mountains, goes through the valleys, compressed, so therefore it heats up and picks up velocity. And you can see how here's the wildfires, and you can see how it pushes the smoke and everything out over the ocean. And again, it's a local regional wind. You don't see these in any place else in the country. It's very common to the West Coast, especially in Southern California. Okay, so we'll stop there and then do ocean currents.